Welcome to the Explainer. Today we're popping the hood on planet Earth. We're going to take a look at how the sun, the oceans, and our atmosphere all work together as this one giant, incredible engine that creates everything from a nice cool breeze to a monster hurricane.
You've probably heard some version of this idea, right? Back in 1972, a meteorologist named Edward Lorenz said this to capture just how beautifully complex and, well, chaotic our atmosphere really is. A tiny, tiny change in one place can have huge, unpredictable effects somewhere else entirely. So, how do you even begin to make sense of all that chaos? Well, it turns out there's a secret. You just have to follow the energy. Seriously, the entire story of our weather and our climate is really just the story of energy from the sun and its incredible journey through our planet.
Okay, so let's start with the absolute heart of it all, the engine itself. It's powered by this constant, massive flow of energy from the sun. And that energy is what drives pretty much everything we experience here on Earth.
Now, it's really easy to think that climate is just, what's happening up in the air. But it's actually way more of a team effort. You've got the atmosphere, the oceans, all the ice, the land itself, and even life. All of it constantly swapping energy and materials to create the world we live in.
Think of all that solar radiation as the fuel for this planetary engine. About half of it actually makes it all the way down to the ground and into the oceans. And this energy doesn't just sit there. Nope, it gets right to work, putting everything into motion.
But before that energy can just bounce back out into space, our atmosphere holds on to some of it. This is the greenhouse effect, and it's a completely natural and absolutely vital process. I mean, without it, Earth would be a frozen rock, way too cold for life as we know it. Here's where it gets really interesting, though. Not all surfaces handle this solar energy the same way. There's this key property called albedo, which is basically just a fancy word for how much sunlight a surface reflects. And the differences from one surface to another, they are huge. For example, take fresh, bright white snow. It's basically the planet's mirror. It reflects a whopping 80% of the sun's energy right back out into space. Now, compare that to, say, sand in a desert. It reflects about a quarter of the energy that hits it, so a lot less. And then you have the deep, dark ocean. It's the complete opposite of snow. It's an incredible energy sponge, absorbing almost everything and reflecting only about 3%. This massive difference between super reflective poles and super absorbent oceans creates this huge energy imbalance across the planet, and that imbalance is what really kicks the whole engine into gear. So because of this really uneven heating, you've got this massive energy surplus in the tropics and a deficit at the poles. The planet's natural response is to try and balance the books. And it does this by creating these giant global conveyor belts of moving air and water. In the atmosphere, this movement creates this amazing three-part circulation system in each hemisphere. Hot air rises up at the equator, travels towards the poles, cools down, sinks, and then flows back. It's this massive continuous loop, always moving heat away from the tropics. But here's a twist. These winds don't travel in a perfectly straight line. Because the Earth is spinning underneath them, their paths appear to curve. This is called the Coriolis effect, and it's what gives our global wind patterns those signature swirls you see on a weather map. And you know what? The oceans have their own version of this conveyor belt too. You have warm surface currents, like the famous Gulf Stream, flowing up towards the poles. Up there, the water gets cold and salty and sinks deep into the ocean. Then it flows all the way back to the tropics. This whole cycle is basically the planet's thermostat. So we've got these gigantic systems of air and water that are always on the move. But what happens when they run into each other? Well, that's where things get really interesting. That's where we get our most dramatic weather. When two totally different types of air, like one is warm and humid and the other is cold and dry, when they meet, they don't just mix. They form a boundary, a line in the sand called a weather front. And this front is basically an atmospheric battleground. A cold front acts like a wedge, aggressively shoving warm air up and out of the way, which often creates sudden, really intense storms. A warm front is a little more gentle. The warm air gradually slides up and over the colder air, which usually gives us that steadier, lighter rain or snow. Okay, now let's scale this idea up, way up. In the Pacific Ocean, under normal conditions, you've got these strong winds that push all the warm surface water over towards Asia. This allows cold water from the deep ocean to rise up along the coast of South America. But then you have El Niño. During an El Niño event, those winds get weak or even reverse, and that huge pool of warm water literally sloshes back across the entire Pacific. This completely flips the script, and it sets off a chain reaction of wild weather disruptions all around the globe. So, we've seen how this engine works on a daily basis. But to really get the full picture, we need to zoom out. We need to look at our daily weather in the much, much longer context of climate over time. One thing is absolutely certain when you look at Earth's history. Our climate is never static. It's always changing. We can see in ice cores and other records these dramatic natural swings, from deep ice ages to periods that were even warmer than today. Change has always been part of the deal. But here's the big but. What's different now is the speed of the change. Since the start of the Industrial Revolution, we've seen this incredibly sharp vertical spike in the amount of carbon dioxide in the atmosphere, supercharging that natural greenhouse effect at a rate the planet just hasn't seen in all of human history. And this rapid warming isn't just a number on a chart. It has real, measurable consequences. The entire system is responding. The global average temperature is climbing, the planet's ice is melting faster and faster, and as a direct result, sea levels are rising. Look, we know the Earth's climate is this incredibly powerful and resilient engine. We know it has always changed. But the sheer pace of the change we're introducing presents a brand new kind of challenge. And that leaves us with a really critical question about the future of this complex system that we all depend on.